This is the review sheet for making use of energy, the third instalment for the specification, but our fourth topic in year 10. So let's have a look. I'm going to start on the top left. It costs £350 to install loft insulation, but it saves £75. What's the payback time? Well, even without this equation, common sense would tell you if it costs £350 and you're saving £75 a year, how much till it pays itself? Well, how many times is 75 going to 350? It goes 4.6. But just in case you want not given this equation, at least I don't think you are. I'm going to press pause and have a look. No, you're definitely not given this. So you either remember it or you just use a little bit of common sense and see how long it's going to take to pay that back. 4.6. I don't think that's difficult. Then we come to the formula for density. So we've got mass, volume, and this is the Greek letter rho, or rho, if it was said in Welsh. R-H-O, I think. I'll have to check on that. But it looks like a lowercase p, and that'll do for me. So your mass is in kilograms, your volume is in meters cubed. That's important, not centimeters cubed, not liters. It's in meters cubed. In physics, we always deal with meters. In mass, in physics, we always deal with kilograms. In chemistry, you'll deal with grams. Density then is kilograms per meter. Oh, I should have put a... Look, how naughty of me. That should be a little 3 there. Then we'll go, why is the fridge... Oh, so these questions are all over the shop. Let's go for... Name the 3 forms of heat transfer first. So you've got conduction, which happens in solids. Convection, which happens in fluids. Which a fluid is something that flows. So liquids and gases are fluids. And then you've got radiation, which is more of a wave. And it can move through a vacuum. So it doesn't need any particles to move. I might go with this diagram now for convection. Draw a labelled convection current here. Well, a convection current is where the warm air rises and it displaces the cooler air. So all the warm air is going to float to the top and all the cool air is going to sink. It's kind of getting pushed down. So it's less dense. This warm air, as particles are given energy, they vibrate and move further apart. And obviously in fluids, there is no fixed space, so they just tend to move apart and they'll go up, and then these ones will come down, the colder ones, and they'll sink and push the other ones. And it's kind of like this is why it's called a current. It's an ever-flowing sort of circle, because they will start cooling down. They will lose energy once they're up the top unless given energy. Like a hot air balloon is a brilliant example of a convection current, and it's constantly giving. They have to keep firing that flame to give it energy, otherwise the balloon will just come back down. So that's a convection current. Now I can go back down to this bit. Why in a fridge is the cooling device placed at the top? Well, now it's obvious, because the warmer air rises to the top of the fridge via convection. All right. Explain how energy then is transferred in radiation. So radiation does not need particles. They can travel through a vacuum, as we said there. Hot objects that will emit radiation. So things like the sun or a fire or even a light bulb gets warmer. It's going to emit radiation. So hot objects emit more radiation, obviously. And cooler objects, they will absorb. So you got hot objects emit, cool objects absorb. And you got 2 different types of these absorbers then. You've got a matte black surface. They're good absorbers. So if you're wearing a dark t-shirt on a hot day, you'll feel yourself get really, really hot. But if you put a white t-shirt on, maybe not so hot, because white or anything shiny are good reflectors, so therefore they won't absorb that heat. A good example is, I don't know if you've ever watched a marathon, but after they've run the race, because they could potentially lose a lot of heat after they stop, because they've just been using all that energy, they'll put these, like a tin foil blanket over them. And what that does is reflects the heat back in. So if it's like a nice blanket, and rather than radiate that heat off, it will reflect back in. And now I feel like I want to go to explain how convection currents occur. Maybe I should have done that before, but it's moving all around here. It was just the way we could fit these boxes in. So explain how convection currents occur. Remember keywords. So particles are free to move around. When heated, So particles gain energy, so they move faster, kind of like I was explaining in that top box up there. The warmer air rises, displacing colder air, which sinks. And then the definition of convection is the process where particles with more kinetic energy, so kinetic is just movement, move from hotter region to colder region. Now, I don't think you've got to remember that definition, but it's a nice definition to have in there. I feel like I want to go to up the top now for conduction. It's the only one we haven't talked about. Talk about radiation, convection, and now we're going to talk about conduction. Energy is transferred via kinetic energy. Particles vibrate and pass energy on to the next particle. It always goes from hot to cold. So if you can imagine standing in line with about 10 people, and the person on the end of the line starts dancing or shaking or even doing a Mexican wave. That is going to pass along energy to the next person, and to the next person, and to the next person. And I know you're going to require a lot of energy for that person on the end to put in to make the whole line move. But that's basically the principle of conduction. So if you're heating one end of the metal or the solid, whatever it is, it's going to start vibrating those particles because heat energy is applied, and then it's slow. It's just eventually going to pass and transfer onto the next particle. It's kind of like a chain reaction. So there's the definition: process where vibrating particles pass extra energy to neighboring particles through kinetic energy, that movement energy. And I think we've covered there pretty much all of the heat energies. And now I need to go back and do a little bit on the insulation. So maybe so I've said 5 ways. You only got to remember 4. So 4 ways to insulate your house. One is loft insulation. That is fiberglass in the attic. Double glazing. Hopefully that's fairly self-explanatory. Cavity wall insulation is when I'm going to talk about that up there. And then draft excluders. So that is like if you've got a gap under your door, just block it up basically. There's a bit more on payback time there. I'll come back to that. Where do I want to go now? Particles. Oh, while we're on the topic of conduction, explain why metals are better conductors. I know this video is a bit all over the shop, but explain why metals are better conductors than metals. And it's because they've got delocalized electrons. They've got free electrons. What that means is, this is the structure of any metal. Okay, so you've got positive, 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 all positives. And then you've got these little electrons, and they're free to move anywhere. And they're going to pass that energy. That's why they're so good. Do you remember we talked about these neighboring particles need to pass energy on for conduction? Well, these electrons can do that really efficiently. That's why they're good conductors of electricity as well. These electrons will carry the charge. And where are we going to go next? Let's go back. Wow, no, let's not go there. So we was talking about insulation, and I did mention cavity wall insulation. And this is how it's. So if you imagine, I got 2 sets of bricks. So you got outer layer of brick, and then you got inner layer of brick. This is how most houses are built. You got 2 layers of brick with a gap between them to reduce conduction. So remember, conduction is through solid. Now you're going to lose heat. And back when they were building just with one skin or one layer of bricks in the old houses, they were finding they were losing a lot of heat energy just through conduction. So they thought, we'll build 2, and they can trap a layer of air inside there. And this is pretty much how double glazing works. You've got a sheet of glass, and you've got a trap layer of air in between, because it's harder to pass that energy then through convection. But you can still lose energy, especially if you've got a really warm house. Your walls are going to get warm. It's going to pass the energy through via conduction. Then it's going to be convection. It's going to get lost somewhere there. And then it's going to be transferred via conduction again. So what they thought, well, let's insulate it. Let's stick this like a fiberglass material. It's like a foam it is. It expands, expanding foam. And that's going to reduce then the convection. So squirting foam between the gaps traps pockets of air, warm air, and it minimizes convection, like I just said. So that's that. How much matter stuff is in something is what we call mass. So there's a difference, and when you get to year 11, you'll be doing a little bit of weight and gravity and mass, and this is where we'll really look at mass. But basically, mass is a measure of how much stuff is in something. So the more stuff that's in something, the more dense it is. The less stuff, so the less particles per centimetre cubed, there's going to be less dense. And you can think of this like water has got a density of 1,000 kilograms per metre cubed. And when you freeze it, it's the same amount of stuff, but it just gets bigger. So it becomes less dense. And that's why ice cubes float on water. Because you've got the same amount of stuff, but a bigger space. So wood typically floats on water because it's less dense. There's less stuff in it than, say, a rock, even though they could be the same size. So this applies to density, and I got a nice question on density by you. If a piece of metal has a mass of 1.2 kilograms and takes up 0.4 meters cubed, what's the density? Well, I'm looking for density, which is the Greek letter rho there, P looks like. So it's M over V, it's 1.2 over 0.4, and that comes out to be 3 kilograms per meter cubed. Now, so you can see here, will it float or sink in water? Explain your answer. I didn't write the explanation, but I'll explain now. So if it's 3 kilograms per meter cubed, and the density of water is well, it should be 1,000 actually. I've made a mistake there. The density of water, right, okay. So the density of water is 1,000 kilograms per meter cubed. I was thinking so it's usually 1 gram per centimeter, that should be there, centimeter cubed. So I need to think about this. I probably need to redo this sheet. But just for now, bear with me. So this answer is going to change now from to sink to float. Because if there's 1,000 kilograms per meter cubed, that's the density of water, then this is only 3, so it's going to float. So by the look there, this is a tiny piece of metal. Yeah, it is. It's a flake of a metal that's just going to float on the water because the density is just not that much compared to water. I was thinking 1 gram per centimetre. That should be a little C in there, centimetre cubed, which is equal to 1,000 kilograms per metre cubed. So just a bit of clarification there, a bit of a mistake. But I've highlighted it, and hopefully that's good enough. So we got, what is the payback time for lagging a boiler? So that's the process where you could do something to your boiler to make it more efficient. Something to do with lining the pipes, I don't know. I'm really not with it. Which costs, and they only cost £40, yet it saves £80 on their bill. Brilliant. So payback time again, installation costs, well, £40, savings, £80, and it's going to take half a year to pay that back. And I think we're on the last one now. Name 3 different temperature scales in a unit. So you won't get a question directly on this. This is just for your knowledge. So you've got degrees Celsius, degrees C, degrees Fahrenheit, which they use in America. And usually when it's 0 degrees C, it becomes 32 degrees Fahrenheit. And that's the scale they start on. I think it goes up in the same increments. I'm not sure. And then you've got the big one then, Kelvin, which is your main one used in science because when you got 0 Kelvin, it's absolute 0. That means that it can't go any lower, whereas our temperature scale, you can be minus 10 degrees Celsius. So 0 Kelvin equals minus 273 degrees Celsius. And that's the lowest you can go. That is as cold as you can get.